Good afternoon, dear students. We are beginning our fourth lecture in a course of time series analysis. The topic of today's lesson is modeling volatility. And we are talking about the fact that the linear models of ARMA, they are not quite correct, not quite fair, because there is such a property, such an effect as nonlinearity in variance. Until now, when we talked about applying the ARMA model to real data, we did not analyze the distribution of the residuals of the ARMA model in any way. Our requirement for these residuals was only that there should be no autocorrelation there, but we did not look at the type of distribution itself. At the same time, when forecasting, when simulating the data, we assumed that these residuals have a normal distribution. A closer look at the type of distribution of these residuals allows us to see that in the vast majority of time series, the residuals after applying the ARMA model do not have normal distribution. Here we have a plot of the empirical distribution of residuals after applying the ARMA model for US inflation. This is the series that we analyzed in previous lecture. And along with this series is the theoretical normal distribution. At a simple glance, it can be seen that there is a significant deviation of the empirical distribution of residuals after the ARMA model from the theoretical normal distribution. These deviations are typically for all time series. It cannot be said that this is a feature related only to the inflation series. These deviations or anomalous effects in the residuals usually come down to three main effects. The first is excess kurtosis. This is a measure of kurtosis, and accordingly, kurtosis is measured by the coefficient k, which with excess kurtosis turn out to be greater than 0. Kurtosis is essentially interpreted as a high probability of small deviations from mean than predicted by the normal distribution. So this is a kurtosis. The second anomalous effect is asymmetry or skewness. Here it is the standard measure of the asymmetry. Asymmetry shows the skewness of the distribution either to the left or to the right. Here, like this, if you visually analyze, you can find a slight shift to the left. In fact, the asymmetric coefficient can be completely different because it takes into account other asymmetric things. Usually, asymmetry recognized as significant if the coefficient S is greater than 0.5 in absolute values. Asymmetry is most widespread in stock markets. If asymmetry is less pronounced in economic time series, then asymmetry is quite common in financial instruments, almost always. And the third anomalous effect in the residuals after applying the ARMA model is called the fat tail effect. Fat tails. In essence, this effect characterizes that the probability that the actual value will be greater than the set values has such exponential function. Well, on the graph, these fat tails, they are here, shown by these bumps, are characterized by the fact that there is a greater probability of significant deviations from the mean than predicted by the normal distribution. These little bumps here are illustration of the fat tails effect. And because of these three effects, which are typical for empirical time series, it is natural that the hypothesis of normality is rejected. Here is the output of Shapiro-Wilk test for the residuals of the ARMA model. It is absolutely clear that this is not normal distribution, and this is a typical thing for time series. How can these anomalies be explained? The first way is to consider that after all, there is residuals that have a non-normal distribution. Then what? What distribution? There are many non-normal distributions in econometric, for instance, distributions of Cauchy, Laplace, student. Indeed, all these can explain both kurtosis and fat tails, where mathematics is quite widely developed. However, these anomalies can also be explained by a normal distribution. Namely, if we take a mixture of normal distributions with different variances. That is, let's conduct such a thought experiment. We have a sample of 1000 data, and this sample is formed as follows. The first 500 items, the first half of the sample, is formed by a normal distribution with low variance, and the second sample is formed due to the normal distribution with high variance. And when we look at such a sample in the aggregate, at its result, we will get both kurtosis and fat tails. This is what the rule is. Thus, it turns out that kurtosis and fat tails, they can essentially be simply explained by heteroskedasticity, that is, differences in variance over the observed interval. This is the property that generates in the theory of time series a further extension of the form of the linear model. I remind you that a linear model is an moving average model or its representation in the form of autoregressive model or as an ARMA model. So this linear model has three theoretical forms. The first form is when the residuals of the model are identical and independently distributed, IID, with mean equal to 0 and some variance. This first form of the linear model we considered in previous lectures, without challenging it critically. Now we understand that it has more plausible alternatives. The second form of the model is that the residuals are independently but not identically distributed, INID, with expectations of 0 and variance depending on time. That is, the variance of the residuals is different. It changes over time. However, the lack correlation of any function from the residuals, that is, the residuals themselves, the square of residuals, the cube of residuals, anything else, this correlation, it will always be insignificant, close to 0. In this case, we can say that this variance just randomly somehow changes in time, and due to this, heteroskedasticity arises. However, there is no regularity in the change in this variance. The third possible form of the model is when the residuals of the ARMA model are dependent but not correlated, the U. That is, these residuals have a distribution with mean parameter 0 and time-dependent sigma squared. But du means that the residuals themselves do not have a lag correlation, but one of the functions of these residuals the square of residuals is usually used because we are interested in the variance, has a lag autocorrelation. That is, the autocorrelation coefficient with a lag for the square of the residuals is not equal to 0. This dependency can be seen through the ACF and the Lewin-Box test, but there are also specific tests. Of these three forms of model, according to most empirical studies, the most plausible is the third form, that is, the residuals of the linear armor model for most empirical time series are dependent but not correlated. And in today's lecture, we will just look at the details this third form of the linear model. The fact that the standard approach to modeling linear model residuals is a third form of the model was firstly found in 1982 by Engel. And this property is called the arch effect, autoregressive conditional heteroskedasticity for time series. There are two ways to test the arch effect. The first method is the easiest, and it recommended that you use it as a part of this course. In essence, this is an autocorrelation function and the application of Lewin-Box test for the squared residuals of armor model. The alternative approach is more complicated, but let's call it, because in the original work by Engel, 1982, where this arch effect was discovered, it was used by it. An auxiliary regression is built. The residuals of model squared depending on the previous residuals with lag y, respectively. This is an autoregressive model for squared residuals. Alpha 0 plus some error. This letter is also called epsilon, only slightly different spelling, but we will call it the Russian letter Y. We name it differently to slightly distinguish the residuals of the model from the ARMA model and from the after arch model. To build such an auxiliary regression, the hypothesis is tested for the simultaneous equality of all coefficients of this model to 0. That is H0, all these regression coefficients equals to 0, and that is, there is no arch effect. Testing this hypothesis can be produced using the Lagrange multiplier test, LM test. Here is how the F statistic is calculated on this test. It is equal to distribution chi squared with the number of degrees of freedom equals to P, an order of arch model. RSSS is the sum of squared residuals of the restricted model, or in other words, the short model. Here the sample mean for epsilon square is used as a short model. And URSSL is our unrestricted sum of squares, or the unconstrained model. In other words, the lone model. Here it is the sum of the squared of the residuals of the unrestricted model that is considered as the sum of this epsilon squared. We will consider these type of tests in more detail in the next lecture when we will talk about the structural breaks. So here we have our first acquaintance with these tests. Now let's move on. The arch model was proposed to describe the arch effect. According to the arch model, the residuals of the original ARMA model are decomposed into some time-dependent standard deviation and standardized residuals Y. These standardized residuals are independent and equally distributed with parameters mean 0 and variance 1. And the standard deviation is a function from time, and it described through the variance function sigma squared as an autoregressive process from epsilon squared with lag y, that is from the residuals of ARMA model squared with lag y. And the order of this model corresponds to the number of lags p plus a alpha 0 coefficient. It is needed to impose restrictions on this model since our variance cannot be negative. Respectively, the restrictions should be that alpha 0 greater than 0, alpha I for all I greater or equal to 0 for all y. There is an alternative description of these independent, identically distributed residuals here. That is, it is not necessary to use the normal distribution here, although the normal distribution already well describes the effect of kurtosis and fat tails because of this theoretical property that we talked about on the last slide. However, to describe the standardized residuals, one can use the standardized student's distribution or a more generalized distribution in the same way. It is called generalized error distribution. It includes many individual distributions as special cases. We'll consider these options using the examples. We will work with you either with the normal distribution for epsilon or with student's distribution to describe these residuals. When we apply the arch model in practice, the first question that arises is how to determine the order P of the arch model. And here it is convenient to use the PAC function for the residuals of the ARMA model. This is because the arch model has property that if we calculate some error and the square of the ARMA residuals minus the variance estimate from arch model, this letter eta, then for this error the expectation is 0 and the lag autocorrelation is also 0 for all lags. And due to this property, the arch model can be rewritten as an ARP process for epsilon squared. And this error here, eta, it becomes the error of the IRP model. That is, in fact, this is equivalent that arch model is usual IRP process for epsilon squared, and they are two equivalent entries. Therefore, PAC is quite suitable for determining the order of the arch model. When we're talking about arch model, we started in depth, and the reason for this is that historically it was the first model that was proposed to model volatility. But the arch model has already known erroneous effects. First, there is a normal error in the arch model, and it doesn't describe kurtosis well. Secondly, the arch model greatly overestimates the volatility forecast. Thirdly, the arch model uses too many parameters, and in more improved versions of the model, the parameters can be saved. Finally, the arch model cannot describe asymmetry in any way. However, since the common principles of constructing are entirely based on the principles of constructing an arch model, they in fact are the development of this model. Then we will dwell on all the principles in detail in the example of the arch model. This slide shows how to estimate the parameters for the arch model. The least square method is no longer suitable. Well, or it fits only very rarely. More precisely, likelihood functions are used to estimate the parameters of the arch model. And these likelihood functions are highly dependent on the assumption of the distribution of the standardized residuals. Note that the arch model parameters are evaluated together with the ARMA model parameters. Therefore, we are already talking about the fact that the model is not just ARMA, but the ARMA plus arch model. About the fact that the evaluation of parameters for ARMA plus arch occurs simultaneously. Well, on the slide here, there are two ways to write conditional likelihood function and its logarithm. The first case is when we assume that residuals, standardized residuals, have a normal distribution. In this case, the likelihood function will be the product of the distribution density of the normal random variable. Since we have an ARMA plus arch score, here we have the squared ARMA error divided by the arch process variance. This is our variance, which is estimated by arch. Well, here we have in the first multiplier, we also get the dispersion of the process by arch. Where we evaluated simply by ARMA, we had this variance constant. So in fact, this estimate did not depend on it, and only the numerator influenced the likelihood function. Therefore, in principle, the conditional likelihood result was exactly equivalent to the least square method. And here, since the variance is a variable value over time, deviations are already obtained, and only the conditional likelihood functions are used, and not the least squares. Taking this function for convenience to get rid of these products gives us the logarithm of the conditional likelihood function, log L. And this is the sum of the observations. The first term is just a constant. It does not affect anything, not any maximum. The second term depends on variance estimate. And the third term depends on the squared ARMA residuals and the model variance on arch estimated. That is, this function must be maximized by choosing the ARMA plus arch parameters. This is under normality of epsilon squared. Oh, sorry, epsilon, standardized epsilon. The second version, when described standardized residuals according to the student's distribution with v degrees of freedom, TV. Here is a student's t distribution with v degrees of freedom. Let's denote it by TV. We have ET. This is a distribution with parameter 0 and 1. And the standard student's distribution is a distribution with variance D. That is, there is a variance for a smaller number of parameters. It is indefinite, and that is Accordingly, in order to calculate the standardized error with a variance of 0 and 1, with a mean 0 and variance 1, we can take only the student's distribution with more than 2 freedom parameters. And accordingly, in order to standardize this value, we must divide the student's distribution with such variance by the standard deviation. Then we will get this standardized value Y, which we will model the error of our ARMA plus ARCH model. Distribution function here is this standardized value. If it has a student's distribution Y, it is written through the gamma distribution. This is the gamma function of the number of student parameters plus 1 divided by 2 divided by gamma function of V divided by 2 divided by square roots V minus 2 multiplied by P. This is our standard student's distribution function, and multiplied by 1 plus standardized error squared multiplied by divided by V minus 2, and here we have the exponent minus V plus 1 divided by 2. This distribution function is valid for more than 2 parameters. Well, this is our standardized residuals, yeah. And we need to write the logarithm of the likelihood and the conditional likelihood function according to the residuals itself, epsilon. Therefore, given the property that epsilon is equal to sigma multiply on standardized epsilon, then we must first divide this distribution into sigma t and the left and the right parts, so that here we had a distribution function epsilon, and here we've got it in the denominator due to this sigma. And the same thing, this function itself epsilon. We replace it with epsilon divided by sigma squared. That is, here we've got the conditional likelihood function already for epsilon. That is for the residuals of the ARMA model. We take the logarithm of the left and right sides, and here we've got the conditional likelihood function, in which we see that this last term depends on the variance and the residuals of ARMA model. Here is the arch variance, here is the ARMA, and here is the first term. It depends only on parameter of student's distribution. Well, this is the distribution of students' parameters. Usually it is from 4 to 8. That is, it is a discrete distribution, and there are not so many values in it. So it is written in textbooks that sometimes they simply choose some a priori parameters of the student's distribution first. That is, V is fixed, and then this maximum likelihood function is maximized, and accordingly this can simply be sorted out for some discrete values of V, and then see at what value of V we get the best mean. This slide provides an example of an arch model for US inflation. This is the example that considered in the first 3 lectures. There, based on the analysis of ARMA processes, we found that the best model is ARMA 1-1, and it implies that the residuals of the model have independent identical distributions. And here we have the model equations based on the application of ARMA with a constant standard deviation. That is, there we estimate it with sigma 00803, the constant standard deviation, and this is the equation. Well, now we know from the lecture that this is not entirely correct, because apparently there is an arch effect. Let's test this arch effect for epsilon squared using the autocorrelation function. Here we have an autocorrelation function. It can be seen that the first leg are correlated here. The 7th, 9th, 10th leg are significantly correlated. So there is significant autocorrelation here. That is, indeed, the arch effect is visually visible through ACF. We check this arch effect with the help of living box test. Well, here it is also clear that guaranteed arch effect, that is autocorrelation, is clearly present here. Now let's try to build an arch model for the variance of our residuals and apply PAC for epsilon squared. And see that the first leg is significant, the second leg is significant. That is, the first two legs are clearly significant, then there is something on the verge. Then again some significance, and 7th, 8th, 9th, 11th legs. That is, this second block can also be taken as a valid alternative H11. Well, the third burst of autocorrelation occurs somewhere on the 15th, 16th period. That is, you can take the third alternative, arch 15. In the third step, we maximize the likelihood function and estimate the parameters of each of these three models under the assumption that the standardized residuals are normal. Here I only showed you outputs, which commands to run in order to get these outputs. I will tell you at the end of the lecture. Plus, there will be a separate practice on using these arch and gauge models in RStudio. That is, as outputs for the first ARMA 1.1 and arch 2 model, we see the distributions norm. This means we use the normal distribution of standardized residuals. Here they are the optimal parameters according to the arch model. That is, these are the mu parameter. This is intercept parameter for ARMA. That is, in fact, mu in our expectation of the analyzed time series. From it is necessary to calculate A0 according to the formula that I given to you. R1 is our autoregression coefficient. MR1 is our coefficient of the MR model. Omega is the output. Omega in the output is equivalent to the exponent alpha 0 in the arch model. Alpha 1 and alpha 2 are the parameters of the arch model. Alpha 1, alpha 2, here we have two parameters. So here you could see the test statistic. It can be seen that all indicators are significant. Everything is fine. Well, here the final value, here the maximum value of log likelihood function, and actual informational criteria are given, which really make our work easier when choosing between a large number of alternative models. The second model is ARMA 1.1 plus Arch 11 model. Here we get everything the same, only 11 parameters, but we see that log likelihood increases significantly when moving from arch 2 to arch 11. Well, the same can be seen that according to all information criteria, arch 11 is better than arch 2. That is, arch 11 is clearly preferred here. So look at the change in the parameters estimates. Here IR1, for example, was 0.9. Here it became 0.9 and minus 0.67. Let's see what ARMA parameters estimate we had in the previous version of the model. Minus 0.89 and minus 0.74. Well, that is, the estimation of the parameters had shifted a little. Please pay attention to this. That is, the addition of the arch effect, it affects the estimates of the parameters of the ARMA model. The third version of model here is ARMA 1.1 plus arch 15. These are 15 coefficients. Here log likelihood increases almost insignificantly, and according to information criteria, we also see that there is no significant improvement. Well, here AIC prefers arch 15, but AIC often overfits the model. By BIC, which is a more conservative criteria, here already arch 11 is preferred. According to the rest of the criteria, arch 15 is also preferred here. But when you have such a slight excess or differences in this information criteria, of course, it is better to look then at the autocorrelation of the residuals and the autocorrelation of the residuals squared. What will we end up with? Here at fourth step, we already checked the standardized residuals for normality and autocorrelation. First of all, we need to check for autocorrelation in order to understand what we choose from the previous version of the model. And here we have such a thing that the living box test on standardized residuals without a square, it shows us that after applying the arch model, autocorrelation occurs in the residuals themselves. Here it is, you can see, this is our ACF. Here we have autocorrelation. This is not good. This is a violation of theoretical purity of the model, but it is a property. But the living box of the residuals in the squared of the ARMA model, more precisely standardized residuals in the squared. This is the squared of standardized residuals. It shows us that there is no autocorrelation here. That is, by applying the arch model here, in my opinion, arch 11 is applied. We have fully included the arch effect in our model, and thus there run no problems. But again, note that by including the arch effect in the model, a fairly wide property is that we've got some error in the autocorrelation of the standardized residuals, and not the square, but the standardized residuals themselves. And what to do with it? When we will talk about the improved model, we will talk about alternatives there. We also look at the distribution itself. Check the standardized residuals for non-normality and see that the kurtosis and fat tails are preserved, but they have become much smaller than on the first slide of today's lecture. Well, the Shapiro-Wilk test is still reject the normal distribution of the residuals, and this may be the reason for us to apply the Stevens function to describe the residuals of the arch model, or use some other types of distribution, or in the end, we can turn a blind eye to this, because in essence, many theoretical effects can be in empirical time series which we have not yet analyzed. Therefore, here, as we were, many turn a blind eye to the deviation from normality. Or then one must show that the student's distribution is indeed better than the normal distribution for describing the residuals. There really are often better information criteria that are able that are provide for us a better log likelihood. But there is some in deviations. Because of this, the ideal model is never obtained. That is, these results obtained with normal residuals, it is quite sufficient to take into account the arch effect. So if you have minor deviations from normality, you can turn a blind eye to this. You can improve it for a very long time, which will be costly, but you can also close your eyes, believing that the required accuracy has been achieved. Here at step 5, we change the assumption that the residuals are normal. See, here we have the same model, Arch2, Arch11, Arch15, but now we have used the student's distribution to model standardized residuals. And we see that the use of student distribution increases log likelihood. It does more credibility for our model, reduce AIC for us and other criteria. There we had 766 and 760 for AIC. For AIC for Arch11. That is here 776 and 770 for big. And they are decreasing here, so it is obvious that the use of students' distribution for standardized residuals has advantages here. This shape coefficient is the coefficient of sharpness of students' distribution. In fact, this is approximately what corresponds to the fact that in theory we had a parameter v, which was the number of degrees of freedom, but this v, it must be discrete, because this student's distribution does not react to immediate options there, and r gives us fractional one. I guess that the fractional part affects the likelihood function itself, but does not affect the student's distribution. But to check this, we need to carefully read the helping R. At step 6, we are already comparing the standardized residuals by ARMA11 plus Arch11 with student's distribution. And we see that empirical distribution is quite close to the distribution student. Although, again, there are some empirical effects that we could not accurately take into account. Here is the effect associated with the autocorrelation of standardized residuals and the autocorrelation of standardized residual squares. We see that the inclusion of the arch effect in the model removes autocorrelation of squared residuals, but instead of this, the autocorrelation of the standardized residuals themselves comes out, which is also not good. And this is also suggests that some kind of incorrectness of the model is present, but we still can't figure out which one. What to do with these inconsistencies? How can you get rid of it? I will say it again a little later, when we go through the next improved version of the model. And I also will have this example. Saying it once is enough. But also, again, it is worth remembering that, after all, we do not include all the effects in real-time series in the model. Therefore, these small autocorrelation splashes, they do not greatly affect the forecasts. There is no way to get rid of them in the end, and it is simply permissible to turn a blind eye to them. Having reviewed this example, now let's see how to build a forecast using the Arch model. This means that Arch model itself allows you to get a forecast of volatility, that is the variance of the model error, and refines the forecast of the original indicator itself, according to which we build the ARMA model. The average prediction of the error variance per step forward is built through an autoregressive model. That is, in fact, this is our Arch model. 2 steps ahead, everything is the same extrapolation. The variance 2 steps ahead is the coefficient A1 multiplied by the prediction of the variance 1 step ahead, plus the sum of the counter from 2 to P, the order of the Arch model, by the coefficient alpha I multiplied by the error of the ARMA model squared with like y, and plus alpha 0. Accordingly, by analogy, by L step ahead, the autoregression from forecast values, and if there is no forecast values but there are historical ones, and then after regression from the historical ones. This is our average central prediction of the error variance from Arch model. But if you want to get an interval forecast of the model error variance and refine the forecast of the initial indicator by including the Arch effect in the model, then you need to do simulation based on the ARMA plus Arch model. No other way. Here the formulas definitely do not exist. Here only Monte Carlo simulation works. From the beginning, it is necessary to make a reservation that with this simulation modeling, the property of the normal of distribution of the forecast error of the original indicator is violated. Our initial indicator is the logarithm of the price level or the price level itself, because in fact we include kurtosis and fat tails in our model. And here we already need to do a large number of simulations and calculate from them not the normal distribution of the interval forecast, but the quantiles of the distribution. Here an example of forecasts. Here is how I came up with the simulated inflation forecasts. These are 4 samples, 4 different simulation forecasts for the same model. The blue line is a simulation forecast only for ARMA, which we built in previous lectures. And the red line is a simulated ARMA plus Arch forecast to make it clearer what effects ARMA plus Arch picks up. You can see that in many cases, ARMA plus Arch gives less dispersion than ARMA. This is essentially equivalent to kurtosis modeling. Somewhere a situation is obtained when the spread is approximately the same. But at the same time, ARMA plus Arch has a non-constant dispersion over time. That is, at first small, then some kind of sharp splash. Then this switch again began to wane, and about the same things happens. Or here, for example, it is clear that this dispersion is not constant, but it does not go so much beyond. Also, there is some cases where ARMA plus Arch shows explosive variance. You see small, then bang. It exploded in different directions, and this is just the main effect of this autoregressive conditional heteroskedasticity, which as a chance we may have in a future time interval. So look please at historical data and what ARMA arch model understand from this, more preciously the arch model understand. From this inflation data, we see that somewhere before World War II, before 1950s, it is obvious that the dispersion of inflation was high. After World War II, the dispersion was low. Arch does not accept this distribution into before and after. Arch analyzes this variance as a single data generation process. Therefore, Arch perceives that the explosion of inflation that was observed before 50s is likely to occur. Well, it is also likely that there will be a situation where there will be a slight fluctuation around the average. That is, the dispersion will be small. Here is the fact that before 50th year, there may be one story, and after the 50th year, there may be a completely different pattern, or in other words, that the process of generating data before 50th year was one, and the process of generating data after the 50th year was different, because of the system as a whole has changed. The infrastructure of the system has changed. Some relations between the participants have changed. More competent leaders have become. Maybe the monetary system has changed, and so on. So this is our inflation. Inflation is obviously related to monetary relations. Here is the fact that this situation could change in 1950, around this time, and Arch model does not take into account it in any way. For such an analysis, when a hypothesis is put forward that at some point in the past data generation process has fundamentally changed, such an analysis required an analysis of the so-called structural breaks. The Arch model does not carry out this analysis of structural breaks, and we will look at how this analysis of structural breaks is carried out in the next lecture. On this slide, we have a 5% interval forecast for ARMA plus Arch, which are obtained using simulation model. And these simulations themselves. As we said, the Arch model add kurtosis and fat tails to the model, and accordingly it often happens that ARMA plus Arch goes approximately around the mean. But the probability of such significant anomalous emission, which are shown here or shown here or here, the probability of these emissions is significantly increased compared to using only the ARMA model. These graphs shows a comparison of ARMA plus Arch interval forecasts with ARMA interval forecasts. Dotted line is our forecast for ARMA. Solid line forecast for ARMA plus Arch. The top two graphs are 5% quantiles. The left graph is the data for the entire history. The right graph is the data enlarged. That is, the left and right graphs are the same, only enlarged. Here you can see that the ARMA plus Arch 5% quantiles slightly pushes interval boundaries in the comparison with the ARMA forecast. Average forecast for both ARMA and ARMA plus Arch is approximately the same, but a small non-systematic error of course arises. And the lower graphs shows the 1% quantile. These 1% quantiles are already better to capturing fat tails, So you can see that the deviations from ARMA 1% quantiles and ARMA plus arch quantiles are already significant. If the 5% quantiles more or less coincided there, then the 1% quantiles, due to the inclusion of this fat tails effect in the model, they show very serious differences here. This is due to the fact that this ARMA plus arch forecast is twitching. That is, this uneven line is associated with the use of simulation modeling and the fact that I did not smooth out these simulation forecasts. In principle, it is recommended to smooth them for a more beautiful picture. This can be done either using a moving average of kernel regression or use other filtering methods. And then it will just be a visually more beautiful effect. This slide shows the prediction of the standard deviation of the residuals based on the arch model. Y-axis, this is our sigma, according to our ARMA plus arch model. That is, in the arch model formula we have sigma squared, and here respectively the root of sigma squared. The blue line is a simulated forecast. Here are 4 variants of this simulation forecasts. The first one is when we have a kurtosis effect, that is, the volatility in the forecast remains low, and the remaining 3 shows options of the explosions of this volatility, how this volatility can explode over time. This brown dotted line here is the forecast sigma according to the ARMA model without the addition of the arch effect. There we had, in my opinion, 8,000s, and here it is sigma 8,000s. That is ARMA without arch effect. It predicts for us that sigma is approximately at the level of the average historical values. Here it is dotted. And by including the arch effect in the model, we got such a forecast for this volatility. This orange line here is the average volatility forecast. The lower quantile of the prediction, the upper quantile of the prediction, and in essence, we predicted volatility more accurately with the arch model. Well, again, since we have already said that the arch model itself does not see any structural breaks, that is, it does not pay attention to the fact that such a high variance was before 1950s, it is natural that the average forecast of this volatility by ARMA plus arch model, it does not take into account this effect of reducing volatility over time. That is, formal model predictions, and here they are blindly arguing that this volatility should rise to about the average level of the previous range. The further the forecast is built, the more likely it is that this volatility will return to some high values. If we also add a structural break here, which we are not talking about now, but we will talk about it in the next lecture, then of course this dispersion prediction according to the arch model should be completely different. While we are analyzing without structural breaks, we want not to complicate things yet. In our course, we gradually increase the difficulty. Everything at once, it is impossible to eat. There are too many features in real data that do not fit into any standard model. This slide of our arch model examples shows the difference in predictions when using a normal distribution of standardized residuals and using a students' t-distribution for these standardized residuals. Solid lines are students' predictions. Dashed lines are based on normal distributions. It can be seen that the predictions by student and normal distributions are approximately the same. Well, there are some minor deviations in the forecasts. However, here is a more or less significant deviations in that the optimistic forecast according to students is going down. It turns out that a significant increase in inflation is less likely. Of course, some shift in the average forecast also exists, such an insignificant one with the margin of error. And then here is to the question that students' distribution of course is better. Let me remind you that we saw through likelihood function, through information criteria, that the standardized student residuals better describe our data. But now we are seeing the values of this fact for forecasts. That is, it is not a significant values for most cases. So see for yourself here. If you approximate and still use only the normal distribution to describe the standardized residuals of the arch process, then this will be a small error. Ideally, of course, it is better to improve at the expense of student, but this will not strong influence on final forecast. Well, the last caveat. At the moment, in the model built by ARMA plus Arch, we still have autocorrelated residuals. Squared residuals do not have autocorrelation, but the residuals themselves, they still have autocorrelation, which means that this specification is not entirely correct. Here we are a little further. When we talk about the improved model, there we will see that we can do with it to make a completely ideal model. So go ahead. Everything that we said earlier for Arch, we can save and transfer exactly to the GARCH model. GARCH is an improved model that was introduced in 1986. Its description is generalized autoregressive conditional heteroscedasticity, and its model already has obvious advantages over the Arch model. That is, everything that we said before about Arch is now directly transferred to GARCH. Everything is one-to-one, but it is now known that GARCH for volatility modeling for all data is much better than Arch. Therefore, the use of Arch is now already an anachronism. Even though the GARCH model was invented over 30 years ago, it is still the basic model. We'll see later in this lecture that there are some alternative volatility model specifications that try to improve on this GARCH model. But in many cases, the GARCH model will remain such a good fundamental base that it is difficult to improve. Let's take a closer look at the GARCH model specification. The ARMA model residuals are decomposed into time-dependent standard deviations, sigma t, and standardized residuals y, which are independent and identically distributed with parameters 0 and 1, all the same. However, the description of the time-dependent variance, sigma squared, itself is an autoregressive process from epsilon squared with lag e. This is the same part that was in Arch, plus an autoregressive component from variance with lag g is added. This is the same variance only with lag g. That is, this second term is in fact an improvement in GARCH in essence, and plus alpha 0. There should be a limit on the parameter gain. Otherwise, GARCH will give us a negative value for the variance, which is anomalous. The constraint on the parameters are alpha 0 above 0, alpha I above or equal to 0, and beta I above or equal to 0. And for the dispersion to be stationarity, we must also have the constraint that the sum of alpha and beta over all I must be less than 1. Otherwise, there will be a non-stationary explosion. The Garch model is equivalent to the ARMA-PK model. The same transformation occurs through the deviation sigma squared from epsilon squared, and for this error value eta. There is a property that the expectations of eta is equal to 0, and the lag correlation of eta is also equal to 0. Accordingly, here we can rewrite the original Garch model, and we will see that the Garch model is equivalent to the ARMA model. That's just the way the coefficients are written. That's before epsilon squared with like I, the coefficient will be equal to alpha plus beta. And before the error eta, the coefficient will be only beta. In fact, this is the same ARIMA. This means that the main advantage of the Garch model is saving of the parameters. That is, on the previous slide, we had 11 or 15 parameters for arch model to be included in the explanation of the arch effect for inflation. And here we see that it is quite possible to cope with 2, 3, and 4 parameters. The order of Garch model can be chosen via extended autocorrelation function for epsilon squared. You can also choose through informational criteria or through the conditional of saving model parameters, while having epsilon squared no autocorrelation. In fact, remember again that the point of using the arch and Garch model is that we in fact just need to pick up some model that includes the arch effect in it, and check that the arch effect included in our model is that there is no autocorrelation for epsilon squared. By the way, for this reason, very often a simple enumerator of Garch model is done. Garch 1.1, Garch 2.1, Garch 1.2, Garch 2.2 is built. Well, it happens maximum Garch 3.3 is reached, and that's it. No one watching normally anymore. This is sufficient to reflect autocorrelation in the model. The likelihood function for the Garch model is exactly the same as the likelihood function for arch. Well, there are some questions related to asymmetry. That is, the Garch model, it really fails to capture the asymmetry in volatility. And it is precisely because of this property that some of the improvements in the Garch model arises. The forecast for the Garch model is based on the extrapolation of the Garch formula. That is, the variance of the one step ahead forecast, sigma t plus 1 squared, is the autoregressive component for the error with like I, and the autoregressive component for the variance with like G. In fact, this is the Garchian equation. We just calculate the variance from the future. For forecasting L step ahead, when the formula is derived, it is taken into account that the squared error is the variance per standardized error. And the Garch model is rewritten in the following form. Here we get this first term, the variance squared and the standardized error square here. and then the same term is added and subtracted to the right side. And what is a plus? This term will, with a plus, goes to the second term. Here we have alpha plus beta multiply legged variance. And what goes here with a minus? Alpha, the one with a leg, a sigma with a leg I, is taken out of brackets, and here we have a standardized error -1. Well, since the average forecast is our expectation, that is, we apply the expectation operator to the left and right parts of the equation, then we've got that the expectation of the standardized error squared -1 is 0. Because the standardized error has variance equal to 1, and the average forecast for all step ahead is equal to the sum of coefficients A plus alpha plus beta for the previous variance, multiply for previous variance. That is, this is the variance which is the previous forecast or the model variance if we have estimated historical data instead of the forecast plus alpha 0. This is our average forecast, respectively. The interval forecast of volatility and the interval forecast of the initial indicator based on the ARMA plus GARCH are obtained. Again, using simulation modeling, and there we already don't have a normal distribution for the initial indicator, just like in the ARCH model. Consider an example of building a GARCH model for US inflation. As I said, I'm just iterating over 4 variants of the GARCH model here with a small number of parameters. This is quite enough. Here they are all versions that are possible. Well, we look at log likelihood, information criteria, and whether this model allows us to remove autocorrelation of residuals or not. That is, here, according to the information criteria, it is clear that GARCH 1.2 is a little better. GARCH 2.1 versus GARCH 1.2 fails, and GARCH 2.2 fails too. Neither IEC nor BEAC compared to GARCH 1.2. That is, according to the GARCH 1.2 information criteria, it is the best model. Here it is the output by the parameters themselves. Mu is the intercept according to ARMA, which is considered as the average value for the analyzed series. IR is the ARMA autoregression coefficient. MA, ARMA moving average coefficient. Omega is our alpha 0 GARCH parameter. When you are seeing in this output that omega is 0, then please use an additional comment to pick up out omega from here, equal to something realistic. Because if you take the full 0 in the Excel or for some manual calculations, even if you see that this 0 turns out to be statistically insignificant for you, then you may have a very strong error in the variance prediction. It is better to pick up these 8, 9 decimal figures from the output and use it in the forecast. Alpha 1 is our GARCH coefficient, and beta 1, beta 2 is also GARCH coefficient with a lag that we had in the formula. And here we have the results of Ljungbox test for standardized residuals and the Ljungbox test for standardized residual squared. That is, just as in previous example with ARCH, we see that autocorrelation appears in the standardized residuals themselves, which is not very good. However, this autocorrelation disappears in the squared residuals. And here we have the Ljungbox test giving a p-value greater than 0.1. That is, there is generally no autocorrelation in the squared residuals. That is, by constructing GARCH1-2 model, we have ensured that the arch effect has disappeared. It turned out to be included in the model. However, here is some kind of autocorrelation of the original residuals or standardized residuals without a square. It arose, and this is not good. An alternative way may be such that we can still choose GARCH1-1, because here you see GARCH1-1 is still one parameter less, and here we also have it. It turns out that there is no autocorrelation in the residuals squared. That is, due to GARCH1-1, in principle, we are quite good at including the arch effect in the model. The same thing, here we have autocorrelation with the residuals themselves. So here are options to choose from. That is, I've seen the approaches of researchers who generally just build GARCH1-1 and that's it. That is, if you follow this approach, this enumerator of information criteria can be completely forgotten. Just take GARCH1-1, just see that the arch effect is turned on by squared standardized residuals, and don't even consider other model. That's what researchers to do. So now you're listening to my fourth lecture. You are already beginning to understand that there are no clear rules on how to do everything. There is some sense that needs to be understood, and how to move within these between similar specifications of models is already the choice of a particular researcher and under his expert responsibility. Well, let's figure out what to do with the fact that our standardized residuals have autocorrelation, which is not very good. And here it is, the fifth version of the model. For this model, ARMA2-1 plus GARCH1-2, I suggest that you also try to include an additional coefficient in the ARMA model. That is, there is no longer any objective criterion on the basis of which we do this. Simply, in essence, when we have the goal of removing autocorrelation from the residuals themselves, that is, increasing the theoretical quantity of the model, we can simply increase the number of parameters of the ARMA model. We just try ARMA2-1, ARMA2-2, ARMA3-2, and if this autocorrelation disappears, then we have succeeded. And from we see that the inclusion of an additional parameter in the ARMA model increases log likelihood, reduces IEC and BEAC. Here we have 768 and 766, and it was 768 and 765 before. That's indeed there is an improvement due to the inclusion of this parameter according to information criteria. Here we have the parameter estimates themselves. Well, here we see that the Lean box test gives us, for standardized residuals, there is no autocorrelation, and also for standardized residual squares that there is no autocorrelation here. That is, we can also say in general that we have already removed the autocorrelation from the residuals themselves. That is, here by adding the one parameter of the autoregression, we've got a decrease in autocorrelation and statistically ideal model. Now the ARMA plus GARCH model for inflation has already been built correctly. This graph shows a comparison of forecasts of ARMA1 and ARMA1-1 plus ARCH15 and ARMA2-1 plus GARCH1-2 models. That is, what do we see? This means that arm plus Garch expands interval compared to ARMA. There is a slight distortion on the average forecast due to the estimation of the parameters in different way. Well, here it is this distortion, it also extends the intervals. The upper forecast, generally speaking, is minimal here. Here it expands over time. The lower forecast is just expanding compared to ARMA. That is, the biggest adjustment, of course, occurs for interval forecast, not for average. On the second graph, here is ARMA plus Garch compared to ARMA plus Arch forecast. And here we see that Arch overestimated these intervals too much, and Garch has an advantage. Firstly, these are fewer parameters, and in second, you see here is what we said about the disadvantage of the Arch model, that is greatly overestimates the forecasts. Indeed, we see this. Garch gives more conservative spreads for these variants. From this graph, we understand that Garch is more correct than Arch model in out-of-sample verification. That is, once again, Arch is already an anachronism, but everything is based on it. The Garch model is the base model. Well, on the bottom graph, you can see the forecast of the standard deviation of the residuals. The dotted line is for Arch model. At the green bottom line, the forecast for Arch and Garch almost the same. The middle and upper forecast for Arch turned out to be too high. That is, Garch gives lower forecast for volatility and an average forecast for volatility. Slowly we are coming to the end. So once again, I must say that Garch is the base model. However, it also has some bugs, some defects. So some improved versions of the Garch have emerged. The first model we are considered is iGarch, or integrated Garch model. Researchers have noticed that in Garch model, coefficient alpha plus beta with the same index are often close to 1. Let's pay attention to the output of our inflation Garch model. We see that alpha is 11 hundredths and beta is approximately 88 hundredths. That is, alpha plus beta gives approximately 1. Here is the property that is very common for the Garch model. This empirical property led to additional research on the properties of the next theoretical specification, and this specification was called the iGarch model, integrated Garch. That is essentially the same Garch, only we have one number of parameters p, and the autoregression coefficients for epsilon squared are equal to y1 minus b, and the autoregression coefficients for sigma squared are equal to b. That's in fact, they made the restrictions of alpha plus beta equals to 1, which reduced the number of degrees of freedom. Some defects of the iGarch model are due to the fact that there is an undefined unconditional variance there. Plus, it is difficult to explain kurtosis. However, these shortcomings are covered by the fact that this iGarch model has a convenient property that the prediction of the error variance L steeper heat is just a constant. which depends on the square of the error and the variance of the error over the last period. That is, here is, in fact, this constant, the coefficients and the value of squared error of the variance for the t period. That is, in essence, the Eigarch model for the forecast uses some given function of the last value of the variance. This property is very convenient because it takes on most of the changes in volatility. It doesn't think of anything. It just takes this volatility as some function of the last value and predicts, and that's it. That is, in addition to the compactness of the model, the forecast turns out to be insensitive to the analysis for structural breaks in the variance. The practice also went such that some researchers simply began to take the Eigarch model without additional justification, and that's it. Even a certain standard in the risk management has appeared up the point that in some risk management packages from investment banks, they simply began to include that we model volatility based on Eigarch 1 and 1 model. Well, simply because it is a very convenient model that does a lot of things. It is because of this convenience in forecasting and saving in parameters that this practice arose. The next alternative to the Garch model is called the exponential Garch model, or Eigarch model. And it allows modeling asymmetries in volatility. Let's look at the specification of this model. Similarly, ARMA residuals are written for the standard deviation plus the standardized error. And to model the standard deviation, such a regression is used. The logarithm of variance squared is alpha 0 plus sums with order p alpha multiplied by this argument. This is our error in absolute value with lag I plus coefficient gamma multiply the lagged error epsilon divided by the standard deviation of the lagged error sigma with lag I. Here in this parameter, asymmetry is recorded here. That is, if we consider alpha multiplying by the nominator here, well, here we omit the standard deviation because it's just a constant. That is, if we consider only alpha multiplied by the numerator, then by converting this, we can see that if our error is positive, then we've got coefficient before the error will be alpha multiply 1 plus gamma. And if the error is negative, then coefficient will be alpha multiply 1 minus gamma. That is, due to this sign change, we have an asymmetry effect that positive risks and negative risks can be measured in different ways. And in reality, the data property generation process may be that these risks are actually different. That is, we've got that the coefficient gamma is the coefficient of asymmetry. Well, the last term of the Eigarch model is an autoregression from the logarithm of sigma squared with lag. Since we are modeling a logarithm here, it's to the form of this autoregression, and this is also a logarithm. This Eigarch is widely used to model the dynamics of stock prices, and also the Garch M setting is widely used for the dynamics of stock prices, which I will talk about a little later. An alternative to Eigarch model is the threshold Garch model, T-Garch, proposed in 1993 by scientists who are represented here on the slide. And This model is also called, according to the capital letters of their names, GGR, GARCH, as a part of packages. This model is also used to model asymmetry, only the symmetry is measured a little differently than in the GARCH model. Likewise, the residual of the ARMA model is signed for the standard deviation and the standardized residuals. As for dispersion, and we already get a such specification, alpha 0 plus sum with the order p, alpha plus gamma multiply n. Moreover, gamma is our asymmetry parameter here. But this one, n, is some threshold that takes the value either 1 or 0. That is, if epsilon below 0, then n equals to 1. That is, there is an effect of asymmetry on negative value. And if epsilon is above 0, then n equals to 0. In fact, if we have in GARCH the influence of the coefficient gamma with plus and minus, depending on whether it is greater than 0 or less than 0, then here we simply have a coefficient gamma enhanced the influence on negative values and does not affect positive ones in any way. Due to this, a slightly different mathematical description occurs. Well, it is clear that all this is multiplied by epsilon squared. Well, plus the autoregression coefficient from the variance itself, it remains unchanged for the GARCH model. The same is taken as for the GARCH model. We also need to have a parameter limit here. In standard T-GARCH model, the threshold is used equal to 0. But in general, to be honest, the threshold can also be sorted out, and there can already be many options for specifying this T-GARCH model. Well, the last specification of the GARCH model, which we will consider in this lecture, is the GARCH-M model. In another way, it is also called GARCH in the mean, GARCH-mean model. Basically, the specification of this model is related to the change of the ARMA model. GARCH-M is widely used for share prices. For stock prices, you know that underlying ARMA model in theory, but not empirically, is ARMA 00. That is random walk for stock price returns. Here we have the ARMA 00 equation. That is simply intercept, or the average return, plus some coefficient gamma, multiplying the error variance sigma squared. That is the inclusion of this term in the mean modification that occurs in the GARCH-M model, GARCH in mean. And the rest of the description is description of volatility. It already happens according to all previous GARCH models. That is, in the same way, the error of this ARMA model is decomposed into a standard deviation sigma and standardized error. And here I have an equation for the error variance in accordance with the usual GARCH model. That is, we have a regular GARCH model. No one will stop you from writing I-GARCH or Ye-GARCH or T-GARCH here instead of the usual GARCH model. That is, here already please modify as you wish. Once again, the very essence of the GARCH-M model is the addition of this coefficient gamma multiply sigma squared to the ARMA equation. Well, again, the theoretical rationale must also exist. So the theoretical rationale here is that the efficient financial markets In efficient financial markets, an increase in volatility can lead to an increase in expected returns. For example, this can happen in the case of rational bubbles. That is, the greater the risk, the greater it seems should be return. Therefore, perhaps some coefficients gamma as a function of risks affects the expected return. Garch M, except for financial markets and stock prices, in my opinion, is not used anywhere else. I haven't heard such news. And also, again, here already this constructor can be easily modeled. That is, other modification of the risk premium are possible. For example, multiply gamma by sigma rather than sigma squared, or gamma to the logarithm of sigma squared. That is, again, this construction can change many times. So that's all. This means that there are quite a lot of other variants of Garch models. I told you the basics. They are enough for you to model. A simple Garch is the basic model. That is, it is the base from which to start. Everything else is extended models. It makes sense to show the advantage every time. I Garch, Y Garch, and T Garch, and Garch in the mean versus simple Garch. Well, now I would like to say a little about the commands themselves, how we build these Garch models in our studio. Once again, to understand, it is necessary to see a seminar on modeling volatility. Here I will list the main commands themselves. First, install the ru-garch package and turn on it. Further, line by line. ugarch spec is a function. This function simply specifies the specification of the Garch model we are working with. So here the spec variable is set to the specification of the Garch model we are working with. It says variance model. This is a variation model, or the variance model is equal to least model we write as Garch. If we want to build a simple Garch, that is a simple Garch. If we want to build an integrated Garch, we write here I Garch. Exponential Garch, right here Y Garch. Threshold Garch, we write here GGR Garch. And instead of as Garch, we also can write any other options. Next, we show the order of the Garch model we want to build. This is the first ratio. This is the second ratio. The first coefficient is our autoregression coefficient. Therefore, if you want to build, for example, arch model, you must take the second coefficient equal to 0. Building arch 15 mean 15 and 0 coefficient here. Building simple Garch 1, 1 will mean coefficient 1 and 1. The second thing is the specification of the average model or ARMA model. So we write ARMA model, ARMA order, and here we enter 2, 1 if we want ARMA to 1 to build, or there 0, 0 if ARMA 0, 0, and so on. In the include mean property, we are including the mean in the estimate of parameters. I recommend that you always set true here, unless there is any theoretical justifications why there should not be an average value in the ARMA model. And this arch M variable is essentially Garchian mean model. That is, if you set true here, this means that it makes the specification of the average values for u with the addition of the coefficient gamma multiply sigma squared that we had in the Garchian model. If you don't want to Garch in mean, then for any specification of Garch model, you simply leave tells here. And the last, the distribution model is the residuals of the model. You are modeling accordingly to the normal distribution norm, or as different you can write std here. Then the residuals will be modeled according to the student's distribution function. That is, norm or std is enough. It is fully specified the Garch model you want to make. The next comment is the Garch model parameter estimation, uGarch fit. This is training the Garch model on the real data. The first parameter is the specification spec that was set above. The second parameter is the data on which you want to train this model. I also had the first CPI differences. This is in the inflation example, so D1 CPI. Well, then you look at the output for this model. The output is given by Garch fit. And it gives you all these tests, the values of the coefficients themselves, Lewin box, autocorrelation tests. There are a lot of things that we looked at. That is, the entire output of Garch is given to us by the command Garch fit. So command KF Garch fit allows you to pick up individual coefficients by Garch fit with a large number of decimal places. That is here where we have only zeros and we need significant numbers in 8 or 9 signs. To see them, we need to do the KF command Garch fit. Well, the next two commands are forecasts. That is, for forecasting using Garch, we use the uGarch forecast command using the Garch fit model and indicate that the forecast should be for here, for example, 299 periods. So command sigma and prognose, it gives us a forecast of the standard deviation for this variable prognose. We'll talk about these commands in more detail in the seminars. So this concludes our lecture. So as a literature, this lecture is grounds on two basic textbooks. This is Tsai Financial Time Series Analysis, Section 3, and Verbeek. This is a textbook, A Guide to Modern Econometrics. It's Section 8 and 9 and 10. Well, if you read the textbook to understand how hard this topic and how much I try to chew to you in much detail as possible, and I hope this lecture will help you to understand the topic. And also please look at the instructions for the uGarch package, because there are many specifications for these Garch models. They are different. And for example, when transferring data from RStudio to Excel, if you need for some reason, you may encounter some anomalous things. For example, the specification of the model in the uGarch package will be a little different than what we study in lectures or what is written in textbooks. Because of this, an error may occur, because everything is written there a little differently. Therefore, there are these instructions, more detailed descriptions of RStudio packages. Please read. Thank you for your attention. Good luck.